got to. I now don't have.
Okay, so everybody, small disclaimer. I have a fever, so that means all of you will have a fever after this weekend, just letting you know. Highly contagious. Either Jaco got it from me or I gave it to Jaco because both of us have this right now. But I decided not to stay home because this is too beautiful not to share with you. So here we are. As you know, we have two things to do today. We went sort of off script last Tuesday because we said, you know, let's do the relativity Lagrangian now, whereas originally it was an exercise for you to solve. But I thought it was good that we did it together. That does mean that we still have some Minkowski space-time diagrams exercises to do, and I would like to do both the Lagrangian ones that we still have and Minkowski. So we really have a two-way tutorial today. I prefer to begin with the Lagrangians. Give the other group the choice. They chose Lagrangians, so let's just stick with that. And let's do it here. Are you getting used to Lagrangians now? No. Okay. It is abstract, isn't it? Yes. It does come with advantages, but the obvious disadvantage is it's difficult to think in terms of Lagrangians. We're going to have a usual issue of where are we going to put people?
I'm going to
just literally in the middle, or? Yeah. Okay, that's fine. I'm happy with all. So the obvious advantage of Lagrangians, or the disadvantage of Lagrangians, is that it's hard to visualize. What the hell is a Lagrangian? That's one. Newtonian physics is much easier to understand, not just because of historical accident that you probably were brought up with this when you first studied your physics or your mechanics, but also because it agrees with what you as a human being walking this earth have an intuition for. You push against things, they start to move. You okay over there? Okay. It's like a movie theater.
It does.
Just out of curiosity, do you prefer the sweet or the salty popcorn?
Sweet and
the caramel one.
The caramel.
Who says sweet? No.
No, sweet and salty.
Thank you.
Sweet and salty. Sweet and salty. Come
Well,
on.
the salty caramel.
Sweet
people,
and
come
salty.
on. Salty
Yes.
caramel.
Not about buckets.
Sweet and salty. Yeah. You have them in back. Sweet and salty.
No, like, you know, some have this salt in the caramel.
No, okay, no, the caramel is something that I understand.
Which is kind of, you have sugar
But
and
without,
salt.
okay, but without the caramel, just popcorn, do you sprinkle sugar over this or you sprinkle
Both. Yeah.
Not sugar.
Like pancakes with cheese and sugar. Okay, I'm gonna shut up now.
Okay, let's go back to early war. Let's go back to physics. One other disclaimer is when I have a fever, one of my ears stops working.
Yeah, that's.
Yeah, I mean, I've never had that before, but it started a couple of years ago, and since then I have that when I have a cold. So that means I literally cannot hear sometimes where people are coming from. But I mean, I recognize your voices, fortunately. So if you don't immediately pick up on your question, just start shouting, especially on that side, because it's going to be this ear. Anyhow, so yes, back to Lagrangians. Advantage. Newton's theorem, it's a scalar, you can do it in generalized coordinates, so that means you're not fixed to a specific set of coordinates, you can use for all kinds of things. Disadvantage, doesn't agree well with intuition, whereas Newtonian physics does. Here's another advantage of Lagrangian physics. It also works for things where Newtonian physics fails. Any kind of physics, as far as we know, can be written in terms of Lagrangians, so also things that do not consist of particles, of masses, or what have you. It's very hard to write down what a Newtonian equation is for an electric field. It is easy to write down, if you have an electric field, how things will move in that electric field. That you can do in Newtonian physics. But how the field itself moves in Newtonian physics, electric field, it's completely silent on that. You need different equations, Maxwell's equations, electrodynamics and such. Lagrangians work for all systems as far as we know. So that's good. So it's very general. Now, let's go through some exercises. So, just curious if we can solve these together, because it's not just mathematics that we're going to do, there's actually physical consequences that we're going to write down. So, we're going to start with a Lagrangian, and I'm not going to specify what this Lagrangian tells you, what kind of physics is described with this thing. I'm just going to say, well, there is a piece of nature, and to describe this piece of nature, you need to know where things are and how fast things are moving. That's all I'm specifying. Now that's very general. Do you agree with me?
Mm-hmm.
Okay. Can you find exceptions to that? Can you find a piece of nature where things do not depend on where things are or how fast they are moving?
Sorry, can you repeat the question?
Yes. Is there a piece of nature that cannot be written maybe as a Lagrangian that depends on where things are and how fast things are moving?
Quantum stuff.
Yes. And quantum stuff, is that the way you phrase it? No, I'm fine with it, it's just I wasn't sure.
Oh yeah.
No.
I said quantum stuff.
Quantum stuff, okay. So why can you not write quantum stuff in this?
Because of the position, maybe? No, because of both.
You
You
can't
cannot
have
know
both,
both at the
yeah.
same time.
Exactly. So quantum mechanics cannot be written in this particular way because it sort of already assumes that you know where particles are and how fast they are moving. You don't know where they are and how fast they are moving. That's exactly what you're trying to solve. But you do know that at the very least there is a function x of t and there is a function v of t. That they follow crisp lines through space, even though you don't know what the crisp lines are. Now that is an assumption that is not true in quantum mechanics because of Heisenberg and such. Uncertainty relations. So does that mean you cannot write quantum mechanics in?
No. We just need to change the L function.
Exactly. So what you do if you want to do quantum mechanics in Lagrangian, well, you don't know where particles are or how fast they are moving, or that you can assign a crisp line in space where they move and how fast they move. That you cannot do. But one thing that you do know for certain in quantum mechanics, and that is that you can. There's a wave function, or let's be. I'm sure in quantum mechanics it was written like this or something like that. That you do know. And you also know that this wave function will have some derivative with respect to time. And then you calculate via all these steps that we're going to do today, you calculate what the Schrödinger function then is, under what rules it follows, and then from there on you can calculate what the probability is that there is at a certain position as such.
In lots of other sources, I've seen they usually write L, x dot t, xt, x dot t, and t.
Yes, an additional t is what you say.
Yeah.
Now your x dot is what I just call v, it's the same thing.
Yeah.
And T
And
is
why
then
is the
explicitly dependent?
Yes, we're going to talk about that. What is the difference between this particular t and the t that is written within there? Okay, so we'll come across the exact point. So I'm just saying that we're going to work with this Lagrangian here without the t. And my question was, is that the most general Lagrangian for pieces of nature? And the answer is not really. You've left out the quantum stuff at this point. But apart from that, this is very general. It could still be an electric field, by the way. Electric fields also have a position. You can say the electric field at this point is so much. And the flow of electric fields from this and here is going to be this and this number. So it would also apply to, say, electric fields or what have you. So, but just not the quantum stuff at this point. So everything we're going to do today and all the rules that we're going to find are going to be very general if you leave the quantum stuff out for now. And just to finish this discussion off, can you do it with quantum stuff? Yes, you can, but then you have to replace the exact crisp lines of how things move through space and time by their Schrödinger functions or their wave functions. All right, so exercise 1a was, well,
We did it in.
yeah, we did it in class, that's true. We had this, I made a claim, I said, well, if you have your Lagrangian, you take its derivative with respect to v, multiply with v, and then subtract the Lagrangian again, then that thing is constant in time. We have done this exercise, this is exactly what we did. Now it just so happened that the recording of the tutorial did not survive. For some reason it recorded only the first 5 minutes, so would it be worthwhile for you to go through this one more time, but very quickly, so you see one more time how that went?
Yeah.
Sure.
And then you also have it on video. So it's a repeat of what we've already done, but it made it good to go through this again, okay? Now, let's not get too hung up on that we call this thing that comes out the energy. Feel free to call it by any other name. The question is it a conserved quantity? That's what we're going to do. Again, we've already done this, but it's good to do a repeat. So let me go very quickly through this. If you want to check whether something is conserved in time, take its time derivative just to show that it is a zero. That means you have to take the time derivative of the LEV v minus L Where does this come from in the first place? Notice theorem. She wrote down this complete theorem for all kinds of observables, and this is just one particular example of it. And now you're going to take the derivative. Now take the derivative of this. That requires the product rule, the differentiation. This gives you this. I'm doing this real time, so if you see me make mistakes, feel free to correct me. Product rule. Derivative of this thing times v, and then the other thing. Still correct? So that takes care of this derivative?
Yeah.
Okay.
Is it
No,
minus divided by the square root? The two functions are L and dv and delta v, no? So if I do the product rule, it should be delta L prime times delta v minus delta L.
No, you do the ratio rule. So if you have a ratio of two things, you take its derivative. That's what you're doing.
Yeah, but we have a ratio to it.
We don't. This is not a ratio. It's a derivative itself.
Okay.
This whole thing is itself a function.
Okay.
It looks like a derivative because of our choice of notation, but it isn't.
Okay.
No, you're right. If this was some function, this was a completely different function, your rule would apply. But it's not a ratio. It's a derivative.
Yeah, that's
And then you have to take the derivative of the L part. Now we talked about this last time. Shania, here's a little bit of your question, namely, how do you take this derivative? Because this thing does not depend on t, you would say, right? I mean, there's no t dependence in there, but there is. It's hidden in the x and v, and that means that you have to apply the chain rule.
Would that be the partial derivative of L by Q?
Well, I call it x, but yes.
X, yes. Into V plus the partial derivative of LV into the acceleration, or x, or V dot, sorry.
Sure.
Yeah.
It's called just dv
V by
dt.
dt, yeah.
Okay, and this then would be dx dt.
Yeah, and my question was, if you don't have t, then you can't add the partial derivative.
That is exactly true. And this is why I told you, wait just a second and we'll get to your question. This part you understand, yes? It does depend on t, your L, in two ways, namely via x, and then the chain rule tells you then you should do this. But it also depends on t via v. And that means you have to do another chain rule, and that's this part. So adding different chain rules is what we call the generalized chain rule. Now, if this were all in the Lagrangian, then we will be done. But yes, and I think you in literature found some examples where apart from t being in the v and the x, there is another t in there that lives outside of v's and t's, v's and x's. This we call an explicit dependence on t. It's a dependency of the Lagrangian on t, has nothing that is not buried within some other function. That means that if that one was there, you would also, and this is again the chain rule, take the derivative with respect to t. But this dl dt is different from that dl dt. Yes?
Yeah.
This is what we call total derivative. It means look for all the t's in the thing, whether they're buried in other functions or not. And this one means look for only that t that is not buried in other functions. That's the difference between the two. Now it so happens that in our exercise this thing isn't there. That means that this earth is going to be 0. But let's go back to it in a second. So we're going to remove it for now because our assumption is that there's no explicit dependence on t. But let's reinstate it in a moment and see what happens.
That's the Euler Lagrange, and you can change that to the dt, d by dt of partial LV.
Yeah.
Yes.
And that's, you can substitute the Euler Lagrange.
Exactly.
Yeah.
Exactly.
And the x over dt is.
Of course, you already see other things drop out, yes?
Yeah.
If we
And
take-
Everything gets cancelled out.
Yeah.
Absolutely. But one of them gets cancelled for a very trivial reason.
Yeah.
The right one.
This one?
Yeah.
This one
And
And
this
that
one.
one.
cancels that one.
Yeah.
without even having to invoke other rules like order cancellation. So that was the old red marker of cancellation that I used there. Now, then you still have this part and that part.
And you're right, it was the solution to find the minimum of the
Yes.
engine.
Exactly, because if you recall, the principle of minimal action tells you that nature chooses your paths, how things move in a particular system of nature, such that the action is minimized. And I postulated, I didn't prove it to you, but I postulated that the statement that this thing is minimized, it's called what we call the action, so that this has the minimal value, is equivalent to saying that L must obey this equation. I did not prove this to you. You already saw a proof somewhere in literature. If all 29 people of the course want to see this, I'm happy to do this during the main course, but it's not that difficult to prove this, by the way. Very quickly, if I want to prove that anything is constant, I have to take its derivative and show that it's equal to 0, yes?
Mm-hmm.
So, let me rephrase. If I want to know what the maximum value is of something, I take its derivative, set it equal to 0, and the x that makes that work is the one that I'm looking for. So what I could do is say, you know, I'm just going to take, I'm looking for the path that makes this thing minimal. I'm going to set this to 0. But it's a little bit more involved than that, because I'm not taking the derivative with respect to x. X itself is a function. It's not a variable, it's a function itself. So it's the same idea, but the calculus that you need is not the calculus, your usual calculus. We'll call it calculus of variations. It's a step up from usual calculus. But the idea is the same thing. Anyway, if you go through this calculation, if you want to see how it's done, I will show you at some point. I might actually make a note and put it on a lane for completeness so people see how that works. It's not too difficult. But you will get this. Okay? So this being minimal, this thing, is equivalent to saying that L should obey this equation. Now, knowing this, that means that if you already know that nature is following the path of minimal action, then this part, that's this thing, is equal to dl dx. So might as well replace this thing by dl dx times the v that was still there. And then I think we're done. dl dx times v, here's dl dx times a v. So these cancel each other out as well. And you get a beautiful 0. So, if you know that nature follows the path of minimal action, and your Lagrangian is not explicitly time dependent, then this thing is always going to be 0. It's constant. Its standard is always going to be 0. Now that's the maths that we already did on Tuesday. Let's go through physical interpretation for a second. There's two things I would like to discuss for a moment. One of them is, let's start here. What do I mean when I say that this thing does not explicitly depend on time? That's a physical statement. There's a statement about physics. The fact that I never included this T here, what does it say about physics, about nature?
That the rules of physics will stay the same no matter how much time has passed.
Exactly. Do you agree with this? If you're not seeing this immediately, let me show it very explicitly. In order to find what nature does, what rules nature follows, you have to take your Lagrangian, put it in here, yes? Do you see that if you add another time dependence to your L, then this side will come out with extra terms all of a sudden? And that means that the laws that come out all of a sudden have this extra time dependence. So your laws of physics are different from the one moment in time to the next. I found out what the laws of physics are today, gravity or so. Try to do the same tomorrow. No, sorry, nature changed its rules. Now the fact that nature doesn't is very much the same thing as saying, okay, there's no explicit time dependence. The only time dependence is built within the x's and v's.
I have a question.
Yes.
So when you say the partial derivative of L by T is 0,
Yes.
what exactly, precisely is the difference with dl by dt?
With this one?
With dl by dt, not the partial.
This one.
Yeah.
The total derivative versus the...
Yeah.
You write each
How would
component.
I mean, it's just conceptually, how would you explain it?
The difference between
The
the
partial derivative and the full derivative.
For me,
This.
for me, if you have dl, you look for every component of dl.
Mhm.
So you will look if it depends on, like here we only have like two functions. So you will look how dt will affect dl on each of its component, and you just sum that to have the total amount. On the first one, you only see how how dl varies on a very specific, if it's time dependent on its very specific function. So if we had dl over delta t, the big like letter, then normally we should have a function that is that it depends on, or it would be 0, because it has no component called t, like no function. It's just like in terms of, if you can see of like it's a function that is built on with other functions, and this function delta t, the function t doesn't exist. There is no explicit function t inside of L, so it's equal to 0. And on the other one, you look for how every parts of the like global function change if you derived on each of its parts dt.
That's for the unsquiggly d, right? That's
For the
straight
small.
D.
The full
Yeah.
derivative. Yeah.
Yeah.
Is that difference clear to everybody? Because it is really important.
Yeah.
Okay. I'm trying to think if I can think of some visual example.
A path or a way. You should look away also, like vectors, for example. If you have to go north and west.
So, so the partial derivative is just for the explicit t, isn't it?
Yes.
Okay. And this is for xt, x dot t.
This one is for all
All of
possible
them,
t's,
okay.
the implicit and explicit one, and
Yeah.
this one is, by definition,
Yeah.
you only look for the explicit t's.
Yeah.
And I was sort of half thinking of an example, but it might be flawed, so bear with me for a moment. But suppose that you are jumping up and down, okay?
Mhm.
That means that how you move in time
Yeah.
is determined by how you are jumping up and down. But suppose at the same time somebody's pulling on your arms and such.
Yeah.
Then that also determines where you are at any moment in time. But that second one
Mhm.
is implicit, because where you are depends on how somebody else is pulling and turning you.
Okay.
Okay?
Okay.
So this is your jumping up and down function. This one tells you how much you are jumping up and down by yourself, and this one tells you how much other people are helping you.
Mhm.
And if I take this derivative, I'm just looking at, regardless of how other people are pulling you while you're jumping up and down, how much you are yourself are jumping up and down. And this one is including all the other pulling and
Yeah.
as well. But
Yeah.
I mean that's it works, right?
It works.
But don't take the metaphor too far. I mean the real mathematical difference is indeed that this one seeks out only explicit time dependencies, and this one all of them, the explicit and the implicit.
My question was kind of why in the second step can you not automatically make dl by dt 0? The full one.
Which one?
This one.
Yeah.
Because there is x of t and vt, and that we don't know if we don't know how like time will be affected. Xt is time dependent and vt is time dependent. Although L isn't, those two functions are.
Okay.
That's a good point. Listen, again, the total derivatives with the straight d's look for all time dependencies that might be in L.
Mhm.
Now there is time dependence in L. It's via x and v. I don't know what they are yet, but
Yeah.
they're probably going to be there. And it also looks for its implicit how much it's explicit time dependence, how much it by itself changes in time. Now that one happens to be 0 in this case.
Yeah. Okay.
yeah, good question.
But is that clear to everybody? It's more mathematics than it is physics. I try to connect it to a physical example. Okay. But there you go.
So if it would have been delta L over delta T, it would have been
Which of the
0.
two?
No, delta, so the first one would be 0, right?
Yes.
Yeah.
Okay.
Exactly.
So mathematically, if x and x dot were x and y, the x and y axis,
Yes.
you're only considering, you can't do it the whole derivative, because this is just one axis and this is just the other, and x dot is just the other. And that's why you have to do them separately to check if each component is zero.
Yes.
Okay.
Yes.
Okay.
What you're talking about now, and for the people not following this, don't worry too much about it. It's a good question,
Yeah.
but don't get confused. I know that the answer is going to fit with your question.
Yeah.
You can make a drawing of how things move, where the one axis,
Yeah.
your x-axis, is indeed your xt, and the other one is your vt.
Yeah.
That's called a phase diagram.
Yeah.
Okay, you might have seen this before in other contexts. And you're right. If you take a total derivative, you're looking how much is L changing due to motion in x direction and in v direction, and possibly by its own motion.
Right.
Yes. All right. So there's that. By the way, I hope at some point in the future we'll have just a full course on just Lagrangian.
Yeah, analytical mechanics.
Yeah, that would be very good. So just for completeness, for people who want to get more of an introduction into this, this is one of the standard textbooks on classical mechanics. It's by Goldstein, and it's a classic. So if you want to read up on these sorts, we're not going to need it as much that we're ever going to need in this particular course, but if you do want to read up on these things, this is a book to go to. Okay, so I'll leave it here for people who want to get the full reference. It also, by the way, has a part on relativistic mechanics, but it's written in somewhat different nomenclature. You mentioned Q and Q dot. That's how usually it's called generalized coordinates and generalized momentum. And I decided to skip that part and immediately call it X and V. But sure. Okay, so this is all clear, yes? And we know what it physically means. It just means the laws of physics do not change from day to day. Now in the liberal arts and science education, somebody will come along and say, philosophy, but who says that nature will not change from day to day? Well, sure, if you want, that's an assumption. Okay, it might be wrong.
But every experiment is based on this assumption.
Yes. Yes.
It worked so far.
It has worked so far, but and yes, it's a highly philosophical thing. But somebody comes along and says, "But who says it will also work tomorrow?" Yes. Okay.
Never mind.
Never mind. let's go with the assumption. Okay. There you go. You're full on YouTube now. Okay.
Yep.
Okay, that's fine.
I just wanted to be on the
No,
same.
you don't care about the book. You just want to have your 5 seconds of fame.
5 seconds of fame.
All right. So there's that. So that makes. Well, I think it's beautiful. Oh, and there was a second thing I wanted to mention. One of them was about the implicit and explicit dependence on T. And here's a discussion that we sort of had a little bit on Tuesday. Namely, this thing that comes out, we've shown that it's conserved for every single Lagrangian that can be written in this way, which is almost all of physics, except for quantum stuff. Why would you call that conserved thing the energy? Why not call it something else?
Because when we translate it into Newton, like physics, it happens to be exactly what we defined as energy.
Exactly.
How do we translate it into Newtonian physics?
We change the Lagrangian.
This is exercise 2 that I will show in a moment. I will give you a Lagrangian that corresponds. If you then ask that Lagrangian, what will nature do, you will find Newtonian mechanics. If you then calculate using that Lagrangian what this thing will be, it will give you exactly what you used to call energy in Newtonian mechanics. And just by extrapolation, we say, you know what, then everything that looks like this is going to be called the energy. It's just labeling. We decided, we found that there's this thing that we call, or that is conserved in time. We can show that it is by historical accident what we used to call energy in Newtonian physics, which is going to call it energy from now on for every system. This is labeling. Now, with the other group, I wanted to get this point across that calling this energy is not a step in physics. It's literally just an exercise in nomenclature. And the way that I did it with the other group was I took one of them and said, suppose you get a baby. Okay? And I'm going to do the same thing to you because it was Zef that I asked. And I said, suppose you and Marina are going to get a baby. So I'm going to ask you the same thing. Suppose you and Zef are going to have a baby.
Okay.
Okay?
She's just okay with it. Okay.
That is one of the other big assumptions of nature. What would you call its baby boy? What are you going to call the baby? I'm going to tell you Mom what Zef would like to call his baby. What would you call the baby?
Max.
Max, okay, he said Zef. He said he's But suppose that you have a baby Max, okay? And then Zef comes along and he says, I think the baby's name is Zef. He said, no, I call it Max. And then I come along and say, but how did you know that the baby's name was Max? And how did you know that the baby's name was Zef? And that's a stupid question, because his name is Max or Zef, because you decided to call it that. There's no deeper law that says whatever came out, well in this case of you, but out of this equation should be called energy or what have you. So it's just by historical accident, we could have called it anything, but because it happened to be something that in history we had to let it be called energy, we're going to call it energy from now on. There's no deeper meaning to it. Just as there's no deeper meaning to having your kid called Max.
Who knows?
Sorry?
Who knows? Maybe there's a deeper meaning.
Yeah,
Yeah, well,
maybe
maybe there's a big
maybe
rule
the
that says
names
all of our names are
combined.
wrong.
Combined is a code. And
Who knows?
Okay, let's move on.
The true name.
So that was the second point I wanted to make. The naming is literally just labeling. So I'm not calling this energy because it's conserved. Oh, but I found something that's conserved. And energy is conserved, so I call it energy. No. And under that argumentation, you might as well call it charge, because charge is also conserved. We call it energy because for this one particular case, it was called energy in the past, so let's stick with that name from now on. That's all there is to it. So in Lagrangian mechanics, to be very puristic, energy is the function or the number that comes out of this particular combination of Lagrangians. Now, in the same way, you can also get a second baby girl, and you call it momentum. That particular baby girl is this thing. Why do you call momentum? Because again, if you do the Lagrangian and you try to get your Newtonian physics back, it just happens to be what we used to call momentum before. Might as well call momentum from now on. So this is what we call momentum.
So it's the first part of the first term of the energy.
Yes. Well, and then you still have to multiply with. It's the first factor of the first part
So
of the energy.
dt of that will be equal to 0
The dt of this?
of yeah.
DBT.
No. That's exactly the question. We have to find out.
We have to prove that it is.
Oh, okay.
But
Or
it
maybe
should be,
that it
right?
isn't.
But
It should be
Yeah,
conserved.
because it's considered.
But if we use the law, we say that delta L over delta X, since it's time dependent, would be equal to 0. Location dependent, X dependent, would be equal to 0. Then we use the relation between delta L over delta X
Yes.
dt. We find that must be also equal to 0, and then we find out it must be equal to.
That's the full answer. So again, this particular thing we call momentum. Okay, the question is it conserved? Now to check that, same exercise as before. You take this thing, and you're going to take its derivative, the total derivative with respect to time. Okay, well, that should be this. And the question is this 0?
Yeah.
Well,
Because it's
Yeah,
equal to
it's
that.
it's this, right?
Yeah, but it's equal to that.
And that's equal to this,
Yeah, which is 0.
0.
under the minimal action. And if the n, this is the condition of the exercise, if your Lagrangian does not explicitly depend on x. So that means that there's no x dependence in there. Then that means that this part is 0.
Yep.
But that means that the time derivative of this thing is 0. So this is 0, which is another way of saying that p must be constant. So under the condition that your Lagrangian is not explicitly x dependent, you will have a conserved momentum. That's what it says. Now let's translate that to physics. We have to do some parsing. This is the math, let's do some physics. Parsing. What does it mean when I say that your Lagrangian is not explicitly x dependent?
It means that no matter what happens, whatever the position, the speed will be the same. So it means a constant.
It
like-
will not be the same. It will not depend on the
Like
time.
if we draw the
Position,
diagram,
yeah.
if we go the diagram, it means that for every x we'll have the same value of vt.
Of v, yes. Well, you already sort of see Newton's first law coming out here, yeah?
Yeah.
If it just happens to be a Lagrangian that describes one moving particle, and in that analogy it's completely clear why this should be the same. But let's not, the statement here is it's generally true. So even if you're not looking at a system where particles are floating about, I mean in that case it's very simple. It's very easy to understand why that is. Now remember what we said, if your Lagrangian is not explicitly time dependent, that it meant if you do the laws of physics at any moment in time you should get the same laws out, not the numbers but the laws themselves.
Ooh.
Suppose that we do the same statement but now replace time by space, the location.
The position. Oh, it's the same. The rule are the same no matter the position.
Yes. No matter where you are going to do your physics, you will find the same laws. To be sure, if I go into experiments here that involve positions, I'm going to find different numbers than when I do the same experiment on the Mount Everest.
But the structure will be the same.
The structure will be the same. The laws will be the same. So, what it says here is that you find that momentum is a conserved quantity in nature under the condition that nature doesn't care where you do your experiments. That is again, let's take the liberal arts and science student here, is an assumption. It might be that 15 billion light years away from here, the laws of physics are different. Might be, we don't know. We work on the assumption that nature doesn't care where you do your experiments. Yes for the numbers, no for the laws themselves. Now, let's make things explicit now, because we have now general statements. Exercise 2 is about, well, let's take one particular Lagrangian. And the Lagrangian, and you have to pretend that you've never seen classical mechanics before, okay? Did you say, hey, look, it's a kinetic energy minus potential energy? Yes, okay, sure, it is. Suppose you've never seen that before. It's just this particular combination of these and x's. I'm not even going to specify what potential energy is, some function of x. Exercise A asks you, I'm not going to write this down, exercise A asks you, just by looking at the Lagrangian, not knowing that this is classical physics, just by the mathematical structure alone, is energy conserved whatever comes out?
Yes.
How can you tell?
No explicit
Time
There is no explicit time dependence. So I just gave you a Lagrangian. You can immediately tell whatever nature does here, it will keep this particular combination that we call energy fixed in time. How about momentum? Is momentum conserved?
I would say so, but I guess since the question is like when
No,
do you
because
use
it's explicitly x dependent.
Yeah, isn't explicitly
Yeah.
dependent on.
but for me it's the same as when we had like VT and
Yeah.
XT, so it's kind of implicit.
Yes.
Oh, is it?
This is yes. So I hear yes and a no, and both of them come with good arguments. And I knew that this was coming, so we have to stay here for a moment, because I'm going to think your argument, I think I heard yours. I'm going to paraphrase you. One argument is, yes, momentum is not going to be conserved. Why? Well, because there's an x dependence in there. So no conserved momentum.
But then isn't x dependent on t?
That's
That we don't know yet.
Do we know that? Is it xt?
well, yes, of course. I mean, in general, your potential energy will depend on where you are, and where you are depends on what moment in time you're looking. So in principle, this is t dependent.
So it's position dependent.
Yeah, but just for clarity's sake, let me give the two arguments that I've heard from the audience. Yes, one argument was, and then we're going to discuss which of the two is the correct one.
Oh, okay.
Just to have everything laid out. One of them is, look, but there is an x dependence in here, so it is x dependent. So that means this rule will not hold. P is not going to be conserved. That's one argument. Another argument is, oh, but wait a minute. There's an x in there, but it's buried in another function.
Yeah.
Just like here, the t was buried in this other function, and here we called it an implicit time dependence.
Yeah.
So there is an implicit space dependence, but an explicit one, and that means, according to this rule, the momentum should be conserved. Both of them sound correct, yes?
Yeah.
The question is,
no,
which
no,
of the two is the correct
Are
one?
you
The last
referring
one.
to the implicit time dependence as the v or the square root of x?
It's not the square root.
I see no square roots.
Oh, that's another v.
It's a
Oh, so
big V,
sorry.
it's
No,
a
this is
function.
it's a v.
Oh,
And the reason I
okay.
put this here, I'm sorry.
Oh,
no.
you also saw
Oh, I'm sorry, guys. Did you think it was a square root?
Yeah.
Oh, I'm sorry. No, I meant
I
I
thought
meant
it was
v.
meant to.
But I wanted to differentiate this V from velocity V, this is potential energy V, so I put this extra thingies on top. But yes, if I draw this out too much, it looks like a square root. This is potential energy, no square roots.
Yeah.
Unless it just so happens that the potential energy is a square root, but I'm keeping it general, okay?
Again, in the differential, what is important is the difference between potential energy. So the position could be different if the difference in potential.
Yeah, but now you're very smuggling in something that you knew about mechanics, and this is
okay,
this is the only thing we know.
Because I had the first argument with the same that is m did as t.
It's not
and then-
explicitly dependent.
I need to get the definition of explicit and implicit straight. So if anything is a function of something else, that something else is implicitly dependent?
That is exactly the root of the question here, isn't it?
Yeah.
Because here we said if P is not explicitly time dependent, but what exactly is meant by explicit? Because here, this we call an explicit time dependence, and we call the T buried within this velocity in this other function, we call it implicit. But now you have something buried within something else. It's
also implicit.
Explicit. So that exactly is the root of the question here.
Also, we can also use the assumption that we used before, saying that the laws of physics are different depending on the position. If it was explicit, since we already know that like normally it isn't changing. The structure will be the same no matter the position.
Yes.
We can also say that even if we don't even if it looks already like implicit, but that could be a further argument saying that
you're completely right, and I think you gave the right answer. And I'm going to paraphrase you in a moment because I fully understand what you mean, but I'm probably going to say it in a somewhat different way. But it's correct what you said. It's exactly correct. I'll give you the answer, and then I'm going to just explain it to you. See if you can follow. This is an explicit x-dependence. Okay. I will tell you why in a moment, but if it is an explicit x-dependence, then that means that this does not hold, and that means momentum is not going to be conserved in this case. Right? Given that this is an explicit x-dependence, then this tells you momentum is not going to be conserved. The big question is, why is it explicit, whereas this x is just as buried in a function as the t was here, and we call this implicit, and we call that one explicit. That is exactly the root of the question here. Does anyone know the answer? It's subtle, but let's see if you can see the answer. Do you understand the question? Yes.
Yeah. Well, what was the big V again? Just
potential energy.
Because you have two pieces of the function and only one of them is
because xt is a function.
Yeah, go ahead. Yes.
Because I think x is a function, whereas t was just like a scalar thing. Like.
No, they're both functions. That x is a function of t, and this big V is a function.
Both are function, but I mean the x, it's x of t. Like there's
this
like
is V of x.
No, but I mean
no, this isn't V of x. This is
it was a simple
it's
variable.
Actually x, but we're just. I mean, okay, I have no idea.
Because t was a variable.
You're on the wrong track. No, it is, but it itself depends again on t.
So is it because t is implicit? No.
We all see the question, yes? It's important that you see the difference. By the way, this is one of the reasons why I would like at some point in the future to have a full Lagrange mechanics course.
So V of x is just a function of x.
But that V of t was also a function.
L is depends on two variables, not variables like variables that depend also on t. So you have like L and then x of t, but then you have V of x.
Yeah, but I hear the words, but I don't see the difference.
But
I'm misunderstanding.
Oh, maybe we can rewrite V in terms of xt. Like if you find
there we go. Okay, listen, we're very close now. If somebody gives you a particular situation, I mean, I gave just a general Lagrangian for whatever situation where V is not specified, yes? In real life, this V is going to be a specified function. For instance, it could be gravity, right? The potential energy due to gravity. That would be something like, with a capital G, something like this, yes? If this were Newtonian energy, this system, Newtonian gravity, then V will be something like this. Yeah. But then you see that L is directly explicitly x-dependent, yes? Now, why is it that I'm able to write out this V in terms of x, but I'm not able here to have written out this x or this v as a function of t.
Is it because you're including the changing in of the Lagrangian by itself by
No,
t?
no, it has nothing to do with this t. It, again,
because
it's-
because you cannot. I think it's just like a way of the way you can. Because they have the same common.
Again, it's subtle, so if you're not really seeing why this is. Listen. Do you know this capital V beforehand when you start your physics?
Oh yeah, they gave us.
Yeah, I mean, it's given, yeah? I mean, if you want to describe Newtonian gravity in my example, then this you already know. Do you already know what this V is as a function of t?
That's what we want to find.
This is what you want to find.
Okay, yeah.
So you're not allowed to say, oh, I already know that it's a function of t in this and this particular way.
It's by definition this one because they gave us like.
This is stated. If you do an exercise in mechanics, in this case, your capital V will be stated. Without this, you have no idea what you
they gave us the definition of V as f being dv over dx. So it means that there is like dx term like.
Well, we will in a moment find that it is a force.
Yeah.
But my main point here is that this capital V tells you something on what system it is that you're describing. In my example, it is gravity. Okay, this thing is completely specified. You know how exactly it depends on x. So you might as well replace it by how it depends on x, and it makes your L a explicit x-dependent function.
In a general exercise, so we have to know that
Of course,
this is known beforehand.
I cannot also know how nature works if it haven't specified what the potential energy is.
Okay.
Without this, you don't know.
So the reason it's explicit is because you can write in terms of x if you know how it was.
Yes, exactly. It's the second part. Thank you. The reason that it's an explicit dependent on x is because per exercise it was already given to you what capital V was, so you know how it depends on x. So that means your L already has an explicit x in there. The reason that you could not do that here, that you say, oh, you know what, I know my
L.
L.
I'm not sure it's dependent on t.
Exactly. Listen, the t that's in this V is implicit.
Yeah.
Why? Because you don't know yet what small v is. That's exactly what you're calculating. So you don't have the opportunity to replace your v by a known function of t and make it explicitly time dependent. You don't know what it is yet. That's exactly what you're looking for. This thing is not what you're looking for. You already know what it is by premise of the exercise.
Yeah, they tell us this function depends directly on t,
Exactly.
on x.
And in this particular way?
Yeah, in this particular way. Whereas when we look for vt and xt and l, it's just an assumption that they depend on time. And what
Yes, it might not be. It might not
but
or it might depend on time in this way or in this way, and you don't know yet in advance which one.
So we just like suggest that.
Yes.
But like we know for sure that potential energy is it acts from a distance of x.
Oh, well, again, this is given by the exercise.
Yeah.
Yeah. Somebody has told you before you start the exercise what this thing is.
So that would make it explicitly dependent, right?
Yes.
But if we know, for example, how it depends on t, like if we know how someone is moving, for
That is a
sure.
very good question. Here's a follow-up question. It's very important. Listen. So I hope you see the difference now. Because you know what piece of nature you're describing, for which you already know the potential energy, then you can just replace this thing by how it depends on x. Now, how it depends on x, that it happens to be this particular form, yes, that's exercise dependent, but that you already know beforehand what this thing is in terms of x, that makes it explicitly x dependent. The only thing you have to do is rewrite your capital V in terms of what it is in terms of x. You cannot do the same thing with small v, because you don't know yet what small v is. Now, here, that's the reason why I cannot just replace this small v by how I know that it depends on t, and make it explicitly time dependent, because you don't know yet how small v depends on t. Now, your question then is, but suppose that you did. Suppose that the exercise happens to be such that you already knew how this thing depended on t.
Yeah.
Now, do you understand that then you don't have to do the exercise anymore? Because if you already know how things move in space, you've already solved the issue.
True. Yeah.
So that is the big difference here.
No, but then if we know Vt, then this would mean that T would be like that L would be explicitly dependent on T.
Yes.
But then the energy would not be conserved.
How would we prove this then?
And this would mean that we would have two completely different physics, one where energy is conserved, the other one when energy is not conserved,
Yeah.
just by the fact that we ourselves know something more.
No,
I think
but
it's if
Go ahead.
we look at the general way, maybe it means that
Or maybe we can just substitute the values and see if
It-
it's conserved or not. Is that
Yeah, maybe.
so if it means that any
Still get
speed
the
will
active
depend on
values
time.
And then see if it's
just
compared.
substitute?
Means like if you know time at any moment at any given time, you can infer the
and
speed.
You can.
Yeah.
So if it was the general case, it means that if we knew that we are able to know for every time the speed that it will have, like for whatever situation it is. If we only have like Vt and it's only time dependent, it means that for whatever, if we have a Lagrangian, a general Lagrangian, it means that all the things that Lagrangian validates, in that specific case, you are able to tell the time of whatever happens. If you know the time, you can say the speed at whatever happens.
Okay. Let's follow this reasoning, right? So, if we know explicitly the dependence of v on t, so we are able to write v as a function of t because it's given, because we find out, because I don't know why, we know it.
Yeah.
Then we can write L in terms of t explicitly, right? Then the delta E over delta t is not anymore 0. So we have a completely different physics because energy is not conserved,
Then-
just by the fact that we know something more.
No,
But
because
then-
We have a different
what you're
physics.
inferring is not that you know something more. You know that you say that what you're inferring is stronger than the small vt. You are implying that for every Lagrangian, for every case, the speed will have that structure. So what you're implying is that you know how every speed possible will change with time, which is impossible.
Wait, say it again.
Because it's a general thing, so it means that it applies to everything. It's very abstract. So when you say that you know v, it doesn't mean that you know v for only one particle. It will mean that you will know for each time the speed of every element of your Lagrangian.
Oh,
So it means that basically you would be able to know every speed at whatever time. You would be able to know whatever speed there is in the universe, or in this specific.
so at the end, what happens?
So in the end, what you say is that if you want to say that we know that the specific v, we never know that specific v. We only know a specific form of v, a specific structure for a specific situation.
Then I know
If
the
we-
energy for
if
the
we
specific
have-
thing.
What?
If we-
Then I know the energy for the specific thing, and it would
Yeah.
say that the energy changes.
Yeah. If we have
So
the
no, it means
values
that you
of
use it.
x
Marina,
and
help
t
me, please.
and v and t, then could we just do this but
I
substitute
think
the
you
values?
and know how to solve yours. But if it's okay with you, you plural, I want to go through this one. Your point is extremely well taken. I think I know how to solve this. Just from my point for it, just that I made a second ago was: do you see why this t is implicit but this x is explicit?
Yeah.
Do you see that difference? Yeah. I think I can solve yours, but I will reserve it for a moment. So Marina's original comment was, but what if you already knew the v? So you knew how it depended on t, just as you knew how this v depended on x. Then all of a sudden, this t in here is now explicitly time dependent, yes? And then Giovanni points comes along, but then something changes here.
Yeah.
I think it will still work out. I will have to go through the math, but I think I can already see what will happen. But the point is, and that's my bigger point here, is if you already know the v, then you have no problem. Then there's literally no exercise. Then you already know how things move, so you don't have to go through the motions. So you have to go through the calculation. So there's two ways out of this. I think one of them is maybe the question then by outset is already ill-posed, because you're putting something in that you already know, but you apply all the mathematics as if you did it, and that something is wrong there. And there's a second way out, I think, and that's by actually going through the mathematics. Just to be very quick, this thing, I will have to work out, I will do this in the break, I think, just to work out how that works, but this is going to be your point. Suppose that you already knew how v worked, and you've replaced all your v's here by whatever function you already knew how it depended on t, then this is immediately going to be 0. Agreed? Because you're going to have a dl dv, but hey, you replace all your v's by t, so there's no t dependence anymore. There's no v dependence anymore, so this is immediately going to be 0. Then the question is d dt of the remaining part, would that be 0? And I think the answer is going to be yes, because you would still have something like this, where this one is probably going to be striped out, but you now have an explicit extra time dependence.
Yeah.
And I think that this is going to cancel this. You would still have a conserved energy, even if you already knew what V was. I'll have to work out the details to see if it works, but this is me thinking on my toes now. Anyway, let's leave it for a moment. For the point now was only, you have to understand the difference between implicit and explicit. Want to know more details? Get the book. Okay? For now, let's go through this exercise. The promise of Lagrangian physics was, you can immediately tell what quantities are going to be conserved. The friendship or
No, we're just
velocity?
conserving momentum.
Yeah.
Okay, good. Here the momentum is conserved, here it wasn't, and there it wasn't. Okay. So, the promise of Lagrangian physics was that you could immediately tell what quantities were conserved just by looking at the thing, even if you didn't know that it was secretly Newtonian mechanics. Energy conserved? No. Momentum? Yes. Energy conserved?
Yes. Energy is conserved.
Yes, energy conserved. No momentum conserved. Okay. Then the second part of the question was, what if this was constant? Energy conserved? Yes.
Yeah.
Because it's still not explicitly time dependent. Is momentum conserved?
Yes.
Yes.
Because when you derive, it's just
Exactly. If it just so happens that this is a constant,
then x doesn't matter.
then x doesn't matter.
No, is a constant with respect to x.
Yes, it might still depend on other things. Maybe it depended on small v or t or whatever.
Okay.
Okay, but in my particular form, I wrote that there's only possibly dependent on x and nothing else. And if it doesn't have that dependence, this is a full constant in any variable. And then this statement says that momentum should be conserved. We'll return to that in a moment when we've gone through the rest of the calculation. So again, this is the promise of Newtonian mechanics, Lagrangian mechanics. It's a lot more difficult if I would just give you a force, as in a form for F, Newtonian mechanics, and ask you to prove the same thing. More difficult. Let's continue. Calculate the expressions for the energy and momentum.
Just plugging the value.
Absolutely. So the energy, well, we already saw there what we have to do. Yeah, you help me. What I did? It should be dl dv times v minus l. What is this? dl over v?
MV.
MV.
Okay, and I also have to take the derivative with. Oh, that's it. dl dv, but I have to multiply it with another
v squared.
Minus what the Lagrangian was. Well, the Lagrangian was given as such. Mv squared minus 1/2 mv squared gives you plus mv squared minus plus v over x. And that's what you used to call Newtonian physics, the total energy. Now, please, do not think, there are some people who do, not amongst you of course, but in general there are people who think as follows. They say, a Lagrangian is just the energy, but with a minus sign in between somewhere. That happens to be the case here. That's certainly not generally the case. So you cannot just take somebody's Lagrangian, spot the minus sign, switch it to plus, now you have the energy. Okay? That does not generally work. It does here by pure accident. Again, going to the nomenclature, because Newton showed that this thing, whatever you call it, is conserved in time, and you do it for Newtonian physics, you find something that you call the energy, might as well call it the energy from now on for all systems. That's it. Momentum. That's the LDV, again, a pure definition. That's MV, yeah? So you might have called it something else. This thing you call by whatever name. You can call it max, you can call it Zeph. But then you find, oh wait a minute, well the metaphor stops at some point, but then you find that this thing, in the particular case of Newtonian mechanics, the Newtonian Lagrangian, gives you what you used to call momentum, might as well call momentum for everything from now on. It's just label, it's just a name. C. And then after this exercise we'll go and have a break, but okay. So the question is, given that this is the Lagrangian, what path will nature make this mass m follow? How do you do this in the first place?
So we use the this relation.
There you go. So let's start with, you all remember this, yes?
Yeah.
If you want to know what nature does, put the Lagrangian in your Lagrange equation. Whatever comes out is what minimizes the action. This is what nature does.
What's the question? Sorry.
The question is, if somebody has given you this Lagrangian, what does nature do? What particles do these mass? What paths do this mass follow? And the answer is, well, the one path, the one x is a function of t and the one v is a function of t, that makes the action minimal. And here we mentioned, oh, but that's mathematically equivalent to say this happens. Now let's go through both sides. dl dx. Can we make sense of this? Here's your L, here's your ddl x.
The only term that will depend will be the big V. But
Yes, this doesn't depend on x. Oh, but wait a minute, if you know x, you also know v, right? So this is sort of dependent on x. Implicitly so, not explicitly so. So, that you have to take the partial derivative. You only look for the explicit. This is why these are curly ones and these are straight ones. It's not by accident. Notation means something here. So look for the explicit dependence, and it's only here. Now, I've never specified, except for the example in a second ago, but never specified what it was, so this is the best you can do.
Yeah.
By the way, we call this, again, it's a definition, we call this the force. The minus derivative of potential energy, how much the potential energy changes through space, is by definition the force. Okay, so that takes care of this side. The other side goes in two steps, two derivatives. The LdV we had already calculated.
Yeah.
It was right here. It's momentum. So this part, this gives you P. Hey, and we knew what P was in our case. It was M times V. Not in general, eh?
Yeah.
This P could be whatever, depending on your system, but for our particular case, that would be MV.
That's force because that's
Yeah.
change in momentum per time.
You have
There you go. It just means change momentum per time, or if you have a constant mass,
Yeah, or V.
and or Lagrange tells you, nature chooses the path such that this equals that, or that this equals that.
Yeah, but we don't have do we have to, because I thought we have to find explicit like solve the differential equation.
No, I can. Well, what you find now here, to be sure, is that nature chooses the path that obeys this.
Yeah.
This is what we have found. If I'm going to ask you now, what is exactly your x?
dt, yeah.
I cannot tell you unless I've given you
Yeah.
capital V. Yeah.
Yeah, but that's why
This is why you got stuck. Okay, I only wanted you to come to get to here. To be sure, have I proven now Newton's second law? I see some nodding. Let me rephrase the question in a different tone of voice.
Yes.
Have I now proven Newton's law? The only thing that I've officially shown is that if this was your Lagrangian, it's the same as if you had started with Newton's law. Unless I can give a very good reason why this was the correct Lagrangian, I have not proven Newton's law. I've just shown that given this Lagrangian, this is what nature does. That's not a proof of Newton's second law. It's just showing the equivalence between this particular mathematical statement and this particular.
There's no way to prove it then.
No, Newton's second law is, well, there's a philosophical discussion there, but it certainly does not follow from these machinations. The only thing I've shown is that if you had Newton's law, you might as well read Newton's law in Newtonian mechanics. That's the same thing as if you had started with Lagrangian physics with this particular Lagrangian. That's the only thing I've shown.
Where did you get the d dt mv equals ma?
That's this thing. I was calculating the right-hand side.
Yeah.
It gives you ddt of dl dv. The LdV we had already seen was m times
Oh,
v.
of course, yeah.
And then you get this. So I've only shown the equivalence between the two mathematical formulations. It's up to experiment to tell you whether this is true. And as far as we know it's true. Very quickly, exercise D. Given your answers B and C, show by taking the time derivative that the energy of this system, we calculate the energy, here it is, that this thing that we've now found for this particular system to be the one that you learned in high school, that it is conserved. Now, you don't really have to prove this, right? Because we've proven it for the general case here. So it certainly should apply here. But it's maybe good to see it happen.
DEDT is 0 because there's no explicit dependence on t.
No, but the DDT is a total derivative.
total.
So you have to look for all the time derivatives in there. But we can very quickly do this. What's the time derivative of this thing, the first part, the kinetic energy part?
MV.
M times V, is that it?
Nowadays it's there, right?
Well, it certainly is M times V, at least, because if you take the derivative with respect to V, that gives you MV. If it were only a derivative with respect to V that we had to take, then it would have been MV, but it's not. We have to take derivative
MV
times the derivative of V itself with respect to time. We call that the acceleration. That's this. How about this? Time derivative.
It only depends on dx, so it should be 0.
No, because I'm asking for the total time derivative and not the partial time derivative. So you have to look for all the possible t dependencies that is in there, including the ones hidden in the x.
So we can say that.
How about we use a chain rule? Take derivative with respect to x first.
Yeah.
We don't know what it is because it depends on what. And then we multiply, that's the chain rule, by the derivative of x with respect to t.
Which is v.
That's its v. Is this 0? As it should. So close, so close.
Oh, yeah. This one, the big V over dx, we know that it's minus.
It is on the board.
It's force.
No, no.
Mm-hmm.
It's
Sure.
Times
It's minus the force.
Minus
And minus the force equals
MA.
MA because we had already proved that.
Yeah.
But it's
But
times V.
Yeah, that's good.
yeah, but then it's V. Both
So
are
it's
times
0,
V.
yeah,
Yeah,
both
the
are
both.
V.
Yeah.
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 So it's
0, right?
Yeah.
Oh, right, yeah.
Then that's equal to 0.
Now this is not surprising because we had already shown that it should come out 0. It's proof for a general case, so it should also hold here, and it does, as an explicit test.
So can I ask something? How did you decide it's gonna be not? It's gonna be explicit derivative, not implicit.
For which?
For
That's-
the big V over dx.
That's like the definition of it
Yeah.
being constant.
You mean why this is a
Yeah.
partial one?
Yeah. Yeah.
That's the definition of the thank you for of the chain rule.
Ah, okay.
Yes. Right. So again, Lagrangian physics. Somebody gives you Lagrangian, you can immediately tell.
But just in the exercise, the way you define f is with a big, like a straight t, no? So could we say that it's the same as f if it's a delta v thing? Because like in the definition you gave, you said f is equal to minus dv over dx, but it's straight d. And here we use partial.
Oh yeah, but in this case it doesn't matter because they originally told you that your v would only depend on x. So that means the explicit and
Okay, so
implicit
there is
time
only-
derivative
okay, yeah,
happens
so-
to be the same thing.
Okay.
Alright, so your foray into Lagrangian physics. There you go. Let's have a break. Let me myself have a coffee.
Oh, yeah, but look where the
I never
so
noticed.
4 over 5 factor and 4 over 5 what's that?
It's 39 degrees.
Like, it should be 39.
You sure it's V over C? I thought it was the other way around.
I mean, that's what I have in my notes, but
Oh.
you can check your notes to be sure.
That's it's like
But V over C just means the C cancels out. If you have 4
Yeah.
over 5
But the other way around as well, but then
yeah,
4 or 5 is ever.
it's smaller or bigger? I mean, does it
What was it again? 'Cause the line is C over V as far as I know. The underline. But it could be turned around.
No, it's 4. So alpha should be 39.
Well, in that case, if that's the case.
Yeah.
Let me check. Of course, it's not tutorial.
Probably this one.
The tutorial night.
It's around 30.
Yeah, alpha is arctangent V over C.
Yeah, so it's 13 degrees, approximately 39 degrees.
39, that's probably
Just think of it. Just take it.
it's probably this one.
That's more.
I'm guessing.
Did you get it?
I don't know, I haven't found any. Like, there are two that are really close,
Could you
but not
give it?
one that is
I
exactly
have
that.
the
Is there one that's definitive?
Yes.
Exactly.
We narrowed it down.
Exactly, yes. There's one that's exactly 4/5 of C.
No, this is. It needs to be a bit more
up.
A bit more curved.
And you get this one.
This one looks not more like it.
But the intercept should be.
Is there one that's a little bit more curved?
Even more.
Little bit?
Yeah.
Well, the next one that you're gonna get is this.
That seems a
It
bit
seems like a
excessive.
lot. Well, 39.
But these are the only two that are plausible. I mean, at least one.
Well, I divided my complete stack into 2 stacks.
Yeah.
That means you've got a part of the
not
stack you
sure.
didn't have that one.
There's a backside.
Wouldn't change because
There's a
backside
backside.
is
Ah, there's a
The
backside.
backside's a different, yes, no, the backside's a
No, wait.
different.
Oh!
Only this one.
Yes.
That explains a lot, because that one was just a bit. This is 39.
39, perfect.
Yeah, we have it. Okay, that's this one.
4/5.
Yeah.
You don't even have to measure the angle.
This is. Wait, what? Oh, of course, that's a way to do it as well.
You can do it by angle, sure.
Yeah, but this is easier.
Yes. But you know that the tangent of the angle is exactly V over C.
Yeah.
So that means dat de overstaande en de aanliggende moeten 4 op 5 zijn. Dus dat wil gewoon meteen aan de hokjes aflezen.
Dit is zo slim, man.
You said no.
Dude.
And now? What do we do now?
Now
Is there,
we
is
celebrate.
there multiple ones?
I mean, yeah, you can just one.
But I mean, is there multiple ones of this so that each
Well,
everyone
I
has
made
one?
10 copies in total.
Oh, he's trying to find them all.
Okay, okay, sure. But you only need one.
Good,
Okay.
okay.
No, but for somebody else, maybe they don't have it.
Well, let's give the next group also something to sit through.
And so it's just counting.
Exactly.
Just turning upward.
Because the angle
Hmm.
is
You want that one?
inverse
Because
tangent
it's
of
there.
V over C, but V over C is really just
I have one here, but I was looking for some for you or for the other.
to the right.
I'm not sure.
Simon,
So if you-
can you give me one?
No, if you just look,
Say right
if the
angle.
line crosses
Well, there's so many.
4 over 5,
There's a
then
lot.
that's
We have one extra.
just by definition of the definition of tangent.
Waivers. Only
Is it perfect?
Yes.
Found it.
Yep. If you go 4 steps to the right, you should go
So you need
5 steps up.
Oh,
Excuse me, the other way around. 4 steps
Okay,
up,
then this is
5 steps to the right. That's the one.
Perfect.
in the whole course box.
Yep.
Yeah, you found it? Yeah, everybody's got a copy?
Yes. Yeah.
Alright, so exercise 6.4 from the book deals with, well, actually pretty straightforward stuff that we have already done via Lorentz transforms, but the question now is, can you also do it with Minkowski diagrams? So I propose to do both. Let's do it via the Minkowski, or the Lorentz transforms, just one more time. We did it a couple of weeks ago, but let's do it one more time for old time's sake, and then see if we can find the same answers, but now in with the Minkowski diagram, right? Same information, because everything in the Minkowski diagram came from the Lorentz transform, so it should give you the same. Just a visual representation of things you already knew. The exercise was this: you have 2 clocks, A and B, and there's a clock C that passes clock A at a certain moment in time, and at some point later it will cross past clock B. This I call the unprimed frame, this I call the primed frame, and it's given in the exercise that in the unprimed frame the 2 clocks A and B are 2 light minutes apart. Now, the book, not expecting you to use Minkowski diagrams, asks you first A and B, like, let's do it in one go. How far apart are these 2 clocks as seen from the primed frame? Now this should be an extremely easy exercise by now. So you tell me, what should I do? So the question is, how far apart are these 2 clocks as seen by clock C? This is literally an exercise from the first tutorial. I don't want the answer. I don't want the number is what I'm saying. But how do you do the exercise? What's the methodology?
How far apart the clocks are?
Yes.
Well, that's the 2c min is the proper distance. 1 over gamma proper distance gives you the distance.
So the Lorentz transforms, Lorentz contraction would give you this, where L0 is the amount of distance in between in the frame where the two clocks are not moving with respect to you. Okay, so that will be this frame. So this is Lorentz contraction, basic stuff. L0 is 2 light minutes. Gamma in this case is 5 over 3. So that gives you 3 over 5 because it's 1 over gamma times 2 c minutes. Yes. And that gives you 6 over 5 c minutes, or if you will, 1 over 2 light minutes. So as seen from the C clock, these two things are closer to each other. So that's easy enough, yeah? This is, the book wanted you to do this as question B, because they first wanted you to calculate how long does it take for clock C to reach clock B, but as seen on the C clock itself. Now there's 2 ways you can do this. Again, this should be very easy for you now. This should be, what, a 2-minute exercise or so. How do you calculate how long it takes as seen on clock C to go from A to B? There's 2 ways.
Well, you take C's velocity, the distance he needs to travel, and from there it's just classical. On Newton, how do you call it?
Yeah,
just high school textbook,
sure.
we say. Yeah.
We're going to, if you can do this stuff by sticking just to one frame. You could go to the C clock frame, that's a primed frame. 2 events. Event 1 is C passes A, event 2 is C passes B. How far the 2 events apart? Well, in this guy's frame, they are 1.2 c minutes apart from each other, and it travels with 4/5 over c. Then you can calculate how long it takes. Because I'm only sticking to one frame, I'm not talking about you go to another frame, you don't have to worry about transforms and such. Indeed, you can just use your high school physics. I get 1.5 minutes. That was one way to do this. This is not the way that the book wanted it, given the order of their exercises, because we first used how far apart they were and then calculated how long that took. But they, as in question B, they asked this number, so they wanted you to have found this number in a different way. What is that different way? Time dilation. What they wanted you to do at A, both of them were correct by the way, there's no preference, it's just the book happened to have chosen this other way that you had to do first, namely, well, stick to the unprimed frame first, see how long it takes there for the clock to go from here to here, and then apply time dilation. So another way to do this is by saying, well, delta t, this everything now seen from the primed frame, you can use your high school physics. Distance to travel is 2 c minutes, that's so 4 over 5 c. Doing the math, 2.5 minutes. So as seen from the unprimed frame, it takes 2.5 minutes to go from here to there. That makes sense, right? It has more distance to travel. And then apply time dilation. Now, you already know by looking at the answers where the gamma should go, but you know, can you also just based on inherent properties of relativity tell how you get from here to here? You have to multiply, divide by gamma. Don't look at the answer.
Yeah, you divide because C has the eigentime.
Yes, you always do this, yes? There's 2 delta t's here, or if you will, this is delta tau. This is the amount of time for the person who sees the events happen at the same location. That's the clock, because event A, him being here and him being there, for him happens at one location. So that means this is delta t prime. We know this number, we calculate it's 2.5. We know gamma, that's 5 over 3. Do the math, and you will get your delta t primed out, and that is the, again this number if you go through the algebra. So 2 ways to calculate the same thing. It's beautiful how it all makes sense. Now going back to our first tutorial where we talked about the muon going through the atmosphere, this is that exercise again. You either look at it from the muon where it has to travel a shorter distance, that is this exercise, or you look from the Earth where it has to follow a bigger difference but experiences time dilation, that's this exercise. Both give you the same answer. Okay, now this was not so much the exercise. Exercise C now is I have to read the exact phrasing. Oh yeah, in C's frame, when A passes C, what time does B read? Now, there's something I don't like about the phrasing of this exercise, and it's somewhat ambiguous. You can read it in two ways. And I don't mean that the physics can be done in two ways. I mean, what exactly it is that they're asking can be written in two ways, can be read in two ways. And when I did the exercise, I at some point wondered, well, is this what they're asking? What I'm doing is correct given this particular reading of the exercise, but is this what they want? Do you see that maybe that there's two ways to read this exercise? It's important that you see, because when I write exercise, I want them to be such that you understand which of the 5 ways I mean.
I mean, from the author's perspective is different, because they explain the rule for which leading clocks lag, so they always use this rule in this case.
Yeah.
So for them it makes sense to ask in this question. Yeah.
That is my reading as well. I think that because they sort of made up, well, they didn't make up, but they came up with the rule via thought experiment.
Yeah.
So I feel that maybe they didn't, that in that the way that they set up their narrative, the exercise is, by extrapolation, has to be read in this particular way. Now, if you haven't read the narrative, you do know relativity, but you haven't read this particular narrative, then the exercise can be read in two ways. Here are the two ways. Listen, I actually made a note of this because I don't want to get into confusion here. You can read it as, what time is it in the primed frame when the unprimed frame sees C pass A? So when C passes A, what time is it in the primed frame? So what time is it on
B?
On B, yes. What you can also say is, okay, now this guy sees this guy pass C, then what time is it on C when that happens? That is a slightly different exercise.
But it says in C's frame, right?
Yeah, but does the C, I know, but does the C in C's frame, does it refer to when A passes C? Is when A passes C that second part?
I feel like it refers to everything, right? Why would it refer to only that part?
Well, it's the second part. What time does B read? There's two ways that how much does it read in B's own frame, or how much time does it read as seen by C? What happens on B? Those are two different exercises.
You can use the fake clock,
That's
the added clock that it's that's the same distance. So when C passes A, this other clock passes B, and then you say that there is 0 time difference in the prime frame, and you calculate.
Yes, that's what I did as well. So again, there are some semantics there, as in both exercises are physically correct exercises, but the question is which one is it that they mean? And I think indeed, exactly as you say, based on their narrative, they expect you to understand which of the two ways that they mean. So I think that what they mean is, what time is it in the unprimed frame, as in what time does clock B read at the moment that the primed frame sees C pass A? So at the moment that C passes A, what time is it on clock B?
In the primed frame.
In the unprimed frame.
In the unprimed frame.
Yes.
But according to the prime frame.
Ah, yeah, okay.
So this, I think, is how they want the exercise to be read. Again, the other way of reading is a perfectly good physical exercise, but I don't think that's the one that they mean. But so I decided to go with that one. Now, we have two events in this particular reading of the exercise. Is oh yeah, this story again. Let's do this. What are these two numbers? We need two events.
1.5 minutes, or like the numbers that we wrote down there, or what?
Yes, well, I'm asking for delta t prime. Oh, that's 1.5 minutes?
Yeah.
Did I do that here as well? Oh, yeah, okay. Well, it boils down again to how do you read the exercise?
Yeah, what do you define into your notes?
Yeah, exactly.
I mean, if you use the two clocks, that would be 0.
Yes.
Yeah.
So what I did, I introduced a clock D here, and the way that I read the exercise was C passes A, and as seen in the prime frame, D passes B, and I'm going to check at what time D passing B occurs as seen on the B clock. Now, because D and C move along with the same velocity, they measure both at the same time. They're synchronized with each other. So that means that event 1, C passing A, and event 2, D passing D, in the prime frame happen at the same moment. So the delta t prime would be 0. How much distance is there in between?
Also 2c minutes.
Sorry, how much?
2c minutes.
1.2 minutes.
Oh yeah, true.
Again, there's ambiguity in how the exercise should be read. So I just made a choice. I'm going to read it as such. She made a note of this, so I won't fall into the same trap next year. Okay, now the question is, what time is it on clock B when D passes B? That's going to be a different number, because C passing A and D passing B happen at the same time in the prime frame, but loss of simultaneity tells you that does not happen at the same time in the unprimed frame. So at the moment that B sees D pass, it's not going to be at the moment that A sees C pass. How do you calculate that number? Yes. Why can't you just use Lorentz contraction or time dilation, just as a check?
Because then you get delta t is 0, because delta t prime is 0. It's kind of reasoning backwards.
Yeah, but that's fine. One way to show that you cannot use time dilation is because it relates one delta t to the other with some gamma in between. But if one of them is going to be 0, then another is going to be 0. So something is wrong there.
They don't happen at the same location.
Exactly. That is the actual full reasoning. The two events do not happen at the same location for the prime person. They're 1.c minutes apart, but they also don't happen at the same location for the unprime person because it's 2c minutes apart. So there's no observable c's happen at the same location. So that means you cannot use time dilation. You have to go with the full Lorentz transforms. But fortunately, we can put some numbers in. There's a gamma. We know what gamma is. That's 5/3. Delta t is 0. Plus minus we inherit from here. The v is 4/5. This is 2c minutes, and all the c's have dropped out at this point. And this is given in minutes.
Isn't it 1.2?
Yeah, it's 1.2.
Yeah.
Plus or minus. It's always the old chestnut.
But there is one mistake,
It should be
because
1.2.
delta x prime is 1.2c minutes.
Yes, you are very right. And 1.1, this I think is 6/5.
Yeah.
That's correct, right?
Yeah.
So 4 times 6 is 24, divided by 3, 8.
It's 24 divided by 18.
By 18.
15, sorry.
It's 8 over.
Oh, sorry. I was. Oh, yeah. I thought 8 minutes. There's something wrong here. No, you're right. So doing the math one more time, we get 24 divided by 15, whatever that number is. So this is how long it takes to steam from the other clock. But is it plus or minus?
It's always a difficult question.
Yes. And usually you cannot really tell by this Lorentz transform, but it is much easier to tell by the delta x Lorentz transforms. There's also plus minus there. Whatever choice you make there is also going to be the same choice here. So you know my trick. I just draw a picture of the two frames. There you go. Event 1, that was when A passes C. So that will be here-ish, yes? Here's clock A, here's clock C. The other, yeah, that's correct. C is floating in that direction in the x prime frame. And at some later moment in time, as seen by the, well, we don't know if it's a later moment in time, but you, at some point, you have clock B here, yes? And along this x prime frame, A clock D is also carried along, yes? Now, at some point, the D will cross here. Here's delta x prime between the two events, because the first event happened in the x prime frame here on this axis, somewhere here-ish. Here. The second event happened here in the x prime frame. Is L x prime a bigger or smaller number than delta x? Here is where the first event happened as seen in the x frame. Here's where it happened as seen in the x prime frame. Here's where both of them see event 2. Which of the two is a bigger number?
Delta x.
Okay, so if you would write down the Lorentz transforms between these two. Forget about the gamma for a second. Plus or minus. In order to make delta x prime come out smaller.
Plus.
Plus. Okay? But if it's a plus over here, it was also a plus over there. There you go. So that means, just to put everything into physical terms, clock B, let's be very clear. Clock A passes C, that happens at t is 0. Then, according to the unprimed frame, they have to wait 24/15 minutes, a plus number, in the future before they see the other one pass by. So in the unprimed frame, C passing A and D passing B happen at the same time. And in the other frame, there's 24/15 minutes in between. By the way, it makes perfect sense, because as seen from this frame, this clock has to travels a shorter distance in the same amount of time, because of Lorentz contraction from here to there. So it means it takes longer before it finally gets to D. Anyway, this was, as you should already be able to solve these exercises.
Yeah, one question on
Yes.
this again. We could have also, without making the drawing, just seen that delta x prime is smaller than delta x, just from the calculations that we did earlier. Or would that be not a good way of talking about this? You know that delta x is 2 c minutes and delta x prime is 1.2 c minutes? And then you see that delta x prime is smaller than delta x.
Yeah, but but these are two different events, yes? Because the events here were when is C at A and when is C at B. And here it's when is C at A and when is D at B. That's two different events. So maybe you're right, maybe it does work out, but you have to be very careful because you're looking at different sets of events. Now, the big question is how to do this in Minkowski space-time diagrams. As you remember, I went a little bit off script last Tuesday, and we don't have a beamer here. So I cannot show you how this is done on a beamed Minkowski space-time diagram. That means I will have to draw it here, or we do it on a piece of paper in front of our noses right now. And I prefer to do the last one because my drawings are going to suck.
Yeah.
I mean, I'm okay with drawing the straight lines and the rotated axis. It's the calibration hyperbolas that worry me. Okay? So, is it okay if we just huddle together here and just